Hello, everyone. This is Professor DePaulo. Welcoming you back to Psych 220 Behavioral Statistics, fully online. And in this week's chapter, we're going to be talking about the T statistic, which is an alternate form of the Z statistic that we talked about in the previous chapters. So the chapter 9 learning outcomes this week involve learning to differentiate between the use of the T statistic versus the z-score hypothesis test that we previously covered, performing hypothesis tests with the t-statistic, and evaluating effect size and confidence intervals using Cohen's d, using r squared, which is the percentage of variance accounted for, and then forming a confidence interval as an alternate means of testing a hypothesis. So T and Z are very similar. And so once you understand the basics of hypothesis testing, that you're trying to reject the null hypothesis and support the alternative or research hypothesis, then it doesn't matter what, actual inferential test that you use, whether it's Z or T. The main difference with T compared to the Z test that we've done previously is that in the Z test, the Z statistic, we know the population standard deviation or the population variance. So we know sigma. Sigma is known, sigma squared is known, right? Um, in the T statistic, we don't know sigma. So if you look at what Z looked like before, you had the standard error of the mean, which was sigma divided by the square root of n. If we don't know sigma, then we need to estimate sigma. And what are we going to estimate sigma based on? We're going to estimate sigma based on the sample, but we're going to be penalized for doing that. So T is more punitive in terms of hypothesis testing than Z is. But it's the same situation. You just flip in a bunch of different, you just exchange a couple of things. You exchange sigma with the sample, standard deviation, and that's basically it. And then T is evaluated on a different distribution than Z is. We're going to be talking about that throughout the chapter here. So remember that Z was equal to the mean of the sample, which is M, minus mu, which is the mean of the population, divided by sigma sub M, which is the standard error of the mean, which is sigma divided by the square root of n. And then we use the normal table to find the critical Z values based on a normal distribution. And you would have a normal distribution whenever the sample size was greater than or equal to 30, or whenever the original distribution was normally distributed, right? Now, a lot of times you didn't know what the original distribution, the population that represents the null hypothesis, you didn't know what that looked like. Uh, but if your sample was over 30, it didn't matter. You were guaranteed to have a normal distribution. In the case of T, we're at even more of a disadvantage because not only do we not know exactly what the population looks like, we don't even know the standard deviation of the population or the variance of the population. So we're kind of penalized for that. Of course, z-scores are the best way z-scores are the best way to test a hypothesis because they have the most power. So it's easier to reject the null hypothesis if you're using a z-test compared to something else, like a t-test. So if you could use a z-test, you want to use a z-test. The problem is that in the real world, we almost never use a z-test. And the reason why we almost never in the real world use a z-test is we don't know the population standard deviation, sigma. We don't know this. So for instance, if the population is first year college students in the country, in the US, I have no idea what sigma is. I mean, if we're looking at, let's say we're looking at math performance of first year college students in the US, I have no idea. I mean, there's a lot of students in the US that are first year college students. I don't have access to that population. It's too big. And therefore, I have no idea what the mean of that population is, nor do I know what the variance of the population is. I can estimate the mean and the variance if I take a sample, especially if the sample is large. That gives me a good estimate of the population mean because the sample mean is an unbiased estimate of the population mean. And as the sample size goes up, the sample mean will become closer and closer to the population mean. And that's known as the law of large numbers. And I can use my sample to estimate the population standard deviation, but that doesn't mean it's going to be a great estimate. But I could do that because most of the time I don't know what the population standard deviation is. In very rare occasions I do, like if I'm dealing with IQ scores, that's been studied so extensively that I know that sigma, the population standard deviation for IQ, is 15. I know that. That's been studied in depth. But a lot of things haven't been studied in depth. So most of the time as a researcher, you don't know this. So if you don't know sigma, you can't use Z, so you must use T instead. And you must use the sample variance as an estimate of the population variance. So you're going to use the sample variance to estimate sigma. But by doing that, you're going to be penalized. It's going to be harder to reject the null hypothesis. So T is an alternative to Z. You can consider T like an approximate Z. Instead of using the standard error of the mean, we're going to estimate the standard error of the mean. So we're going to use the sample variance to estimate the population variance and then compute the standard error and estimated standard error using the sample variance. And we're going to call this S sub m, the estimated standard error of the mean based on the sample variance. So we use S squared, which is the variance of the sample, to estimate sigma squared, which is the variance of the population. And the estimated standard error is going to be simply S divided by the square root of n. So when we did z-score, we saw sigma divided by square root of n. Now we're using S divided by square root of n. Or the text will often write the square root of S squared over n, which is equivalent to S over square root of n. So if I just take the square root of the top and the bottom, I get S over square root of n. So however you want to write it, it's the same thing. We're using the sample variance to estimate the population variance, and then we're computing the estimated standard error of the mean. So if you don't know sigma, if you don't know the population standard deviation or sigma squared, the population variance, you must use the sample as an estimate, even though it is going to cost you something. It's going to cost you power, statistical power. It's going to make it a little harder to reject the null hypothesis. You can still test the hypothesis, it just makes it a little harder to reject the null using T instead of Z. So here's what T looks like. T is equal to the mean of the sample, which is M, minus the mean of the population, which is mu, divided by S sub m, which is the estimated standard error of the mean. So it looks exactly like the z-test. The only difference here is the denominator, where instead of sigma, I'm using S. That's the only difference. It's the same formula, which is one number changed. So computation of the sample variance requires computation of the sample mean first. So we remember how we computed mean and variance back a few chapters ago, right? And there were two, you could either calculate variance using the deviation scores or using the computational formula that I showed both ways. We come to this idea of degrees of freedom again. Degrees of freedom are the number of scores in your sample free to vary. And if you know that the sum of the deviation scores must equal 0, then only n minus 1 of the scores in your sample are free to vary. So therefore, the degrees of freedom for your sample is always equal to n minus 1. It's a little bit of a tricky definition of degrees of freedom, but you really only have to know that degrees of freedom is n minus 1 if you're dealing with one sample. For every parameter you're estimating, in this case, if we're using t, we're using the sample standard deviation to estimate the population standard deviation. So we're estimating one parameter. So for every parameter we're estimating, we're going to lose 1 degree of freedom. So if we're doing one sample and we're estimating 1 sigma, we're going to lose 1 degree of freedom. That's why you have n minus 1 here. If I have 2 samples and I'm estimating 2 standard deviations, population standard deviations, I would lose 2 degrees of freedom. And you're going to see that when we get to the independent groups t-test. The independent groups t-test is going to have n minus 2 degrees of freedom, whereas the single sample t-test that we're talking about in this chapter, we're only estimating 1 parameter, so we're going to have n minus 1 degrees of freedom. And the difference between Z and T is the distribution. Z only has one distribution. There's only one table. There's only one normal curve. T has a different curve for every different degree of freedom. And since degrees of freedom are related to sample size, every sample size is going to have a different curve. And so that's why they call this a family of distributions. So there's a different t-curve for every different degree of freedom / sample size. As your degrees of freedom get larger, t will approximate z. So they'll be identical. So if you had an infinity sample size, right? So as your sample size goes to infinity, t will become exactly equal to z. So your t distribution will be the exact same as the normal distribution. You can see from this picture when the degrees of freedom is 5, you see the curve is kind of flatter in the middle, and it's also wider in the tails, fatter in the tails. That's not a good situation because that makes it harder to reject the null hypothesis that way, because you have a higher probability in the tails. As the degrees of freedom go up to 20, you see that it's getting closer and closer to what the normal distribution looks like. As you get to infinity, it'll be exactly the same. But you don't have to have infinity sample size because obviously that's not realistic. You're not going to have a sample size of infinity. You could have a large sample size. So once you get over 30, the t distribution is going to be very, very close to the z distribution. Once you get to 100 sample size, it's almost identical. It really is very, very almost identical. It's off by a couple of decimal points. So as the degrees of freedom goes up, as your sample size increases, your degrees of freedom increase, t is going to approximate z. It's going to become normal. And technically at infinity, t will be equal to z. The moral of the story is make sure you have a big enough sample because otherwise you're going to be penalized severely. With a small sample like 5, degrees of freedom of 5, which is the sample size of 6, you're going to have a huge penalty in terms of rejecting the null hypothesis. So you need big samples. The same thing I've been saying every week is get your sample sizes up so that you can then reject the null hypothesis easier or more easily. As I mentioned, that there's a different t distribution for every degree of freedom. And there's a different degree of freedom for every different sample size because it's n minus 1 degrees of freedom. As your degrees of freedom goes up, you approximate the normal distribution. But if you have smaller degrees of freedom, you're going to have much fatter tails of the distribution and a much more flatter middle of the distribution, which is going to make it really hard to reject the null hypothesis. And there's a table of t in your textbook, in your appendix, that will enable you to find the critical values. Remember those critical values of z that we talked about last time? For the one-tailed test, it was 1.645, which is alpha of 0.05. And for the two-tailed test, it was plus or minus 1.96. And then if you drop to an alpha of 0.01, for the one-tailed test, it was 2.33. And for the two-tailed test, it was plus or minus 2.58. So those are the common critical values for 0.05 and 0.01 for Z, and they always stay the same. For T, your critical values of the T distribution will depend on your degrees of freedom, and it will depend on if you're doing a one or two tail test and your alpha level. And the table will give you the critical values that you need to then compare to see if you reject the null or fail to reject the null. So here's the T formula. Sample mean minus population mean, which is the same as Z, m minus mu, over the estimated standard error of the mean, which is S sub m. And if you break that down more, S sub m equals S divided by square root of n. So you're just using the sample standard deviation to estimate the population standard deviation. And that's why this is called the estimated standard error of the mean. But the formula is basically the same as Z. And if you're doing a Z-test for your research, you have a population that represents the null hypothesis, and the mean of that population here is 30. That's the no effect, right? This is before treatment, so basically there's no effect here. Then you get a sample, and you give the sample some kind of treatment, and then you measure the mean of the sample. And we want to see if the mean of the sample is different than the mean of the population that gets no treatment. That basically, the no treatment group represents the null hypothesis. And you want to say that there's a statistical difference. That's the same thing we did with the z-test, except here we don't know sigma, so we have to estimate sigma. So you're going to state the null and the alternative. The null means there's no difference or no effect. The alternative means that there is a difference, there is an effect, and your alternative can be one-tailed, which is directional, or it could be two-tailed, which is non-directional. As a researcher, I prefer two-tailed because that's what's kind of expected, unless you have a serious reason to believe that you're going to use a one-tailed test. You have to be almost certain that the effect will be in one particular direction. You're then going to calculate the t-value and look up the critical t in the table, depending on your degrees of freedom and your alpha level, and whether it's directional or non-directional. And then you're going to compare. You're going to make a decision. Is my obtained t-value more extreme than the critical value? And if your obtained t-value is more extreme than your critical value, you're going to reject. If it's not more extreme, you're going to fail to reject. So the same logic as z-test. So this is what a t distribution looks like for a small sample size. So here's a sample size of 9, which means that there's 8 degrees of freedom. As you can tell by the curve, it's flatter in the middle compared to the normal distribution. The normal distribution would be more peaked in the middle. But the t distribution for a small sample like this is flatter in the middle and thicker in the tails. And because the tails are thicker, look at the critical values. The critical value is 2.306 at an alpha of 0.05. It's also negative 2.306, so this is non-directional. It's two-tailed. If this was a normal distribution at 0.05, the critical value would be 1.96 and negative 1.96. So you can see that 2.3 is a lot bigger than 1.96. So it's much harder to reject the null hypothesis with this t distribution than it would be with the normal distribution because the critical values are bigger. because there's more in the tail. That's why the critical values are bigger. There's more, you know, there's a higher probability in the tails. So if you could use Z, use Z. In research, you really can't use Z. You almost always use T. If you're going to use T, make sure you have a big enough sample. Don't have a sample like in this example. The sample is 9 and the degrees of freedom are 8. That's way too small. And because it's so small, you're getting penalized here. It's going to be really hard to reject the null hypothesis. Some of the assumptions of the t-test are that you're dealing with independent events or observations, which basically means you can't have the same person count twice in your sample. So if you have one individual in your sample, they can only count once. You can't just, replace them and bring them back later. That's basically what independence means, that the people in your sample are not related and they're not the same, basically. That's pretty easy to do with sampling. You only have one person. Each person can take the test or take the treatment once. You don't want to have them, repeat anything. And also the population that you're sampling from must be normal. With large enough samples greater than or equal to 30, this assumption is good. It's met. You're basically guaranteed to have normality. If you have a really small sample, then you have to be careful here. But this assumption is pretty robust, which basically means that unless you have a really, really small sample or the population is extremely skewed, non-normal, you're okay with this. Okay. There's a lot of robustness to the statistics that we're doing, which means you could break the rule. You could break the rule pretty well. You just can't excessively break the rule. You know what I'm saying? You can't have a real tiny sample or a really, really heavily skewed population, because that would, it wouldn't be robust enough to deal with those problems, right? But if the population is even, not normal, but a little bit off, a little bit skewed, you'll be fine. If your sample is large, you're definitely fine. So the moral of the story, once again, is get a large sample. If you get a large sample, you don't have to worry about any of this stuff. But even with a smaller sample, the robustness of the tests make this kind of not a problem, as long as your sample is independent. So as long as you're not, using the same individual and counting them multiple times in your sample, which you're not going to do anyway. As long as you're not doing that, you're fine. Now, in terms of the standard error of the mean, which is in the denominator of your t-test, right? If you want to keep that standard error of the mean small, which is basically the goal of researchers, because if they keep that denominator small, then the t-test will be big, and you'll be able to reject the null hypothesis. So to keep that denominator small, you want to increase the sample size. That will reduce the error, the standard error. And you also want to decrease the variance if possible. So the greater the variability or the variance, the larger the standard error is going to be. So you want to keep that variance on a relatively small scale. Try to keep it smaller. Let's take a look at a couple of questions here. So when n is small, when your sample is small, less than 30, the t-distribution is going to be flatter and more spread out than the z. Right? So when you have a small sample, you're going to have a flat t-distribution with thicker tails, and it's going to be a lot harder to reject the null hypothesis. So here the answer obviously is B. The t-distribution is flatter and more spread out, has thicker tails compared to the z-distribution when your sample is small, especially smaller than 30. The smaller the sample, the flatter it is and the thicker the tails in the t-distribution, and therefore the harder it is to reject the null. So get a bigger sample. See, that's one thing that researchers usually have an easy time with, is getting a sample. There's no reason to have a sample less than 30 unless you're doing very expensive research or you're dealing with very rare conditions or phenomenon. Uh, and then in some cases, like tricky longitudinal studies where you have people do it week after week after week, then you have a lot of dropouts. So you have to be careful that you're not going to go too small with the sample. But other than that, I mean, there's no reason to have samples less than 30. It's not very difficult to get 30 people in your study, even if you have to pay them. It's not that expensive. Uh, if you paid them $10 each, you're talking about $300. And that might seem like a lot of money, but in terms of research, it's not a lot of money. Uh, there's lots of grants out there if your research is good enough and trendy enough for what they're giving away. Let's look at some true false here. By chance, two samples selected from the same population have the sample size of 36 and the same mean. Will they have the same t statistic, I should say? Well, we don't know because just because they have the same mean and the same sample size doesn't mean they're going to have the same variance. And the variance of the sample is what's going to determine the value of t, in addition to the mean and the sample size. So you got to be careful with the variance. So we don't know yet. The variances will probably be different, and therefore the t values will be different. And the second one, compared to a z-score hypothesis test with a t statistic, requires less information about the population. That's true because if you're using a z-score, you need to know sigma. If you're using a t statistic, you don't need to use sigma. You're going to estimate sigma using the population variance and standard deviation. So the t statistic does not require the population standard deviation, and you got to be careful what the variances are in order to determine what the z-score is. So these are pretty straightforward based on the formulas. Now, if you test your hypothesis, even if you reject the null, you still should determine the effect size. The effect size is the true effect of the independent variable that's independent of the sample size. So you should always have an effect size measure after your, statistical test of the null hypothesis. Because there are situations where there's a very small effect, but it becomes statistically significant because the population is very large. And so it's not as important because it's being driven by the huge sample size. So always calculate the effect size to know how strong is your independent variable, how strong is your treatment, or whatever you're manipulating, how much of an effect is it having. That's what the effect size will tell you, regardless of the sample size. And we use Cohen's d, like we did in the previous chapter. And Cohen's d is simply the mean difference divided by the sample standard deviation. In this case, we're using a sample standard deviation instead of the population. So it's m minus mu over s. So in this case, we want the numerator to be larger and the denominator to be smaller if possible. We could also calculate effect size using r squared, which is the correlation coefficient, the Pearson r squared. And we'll be talking about this later on in the course, the correlation coefficient. But basically, what this r squared measure here is the percentage of variance accounted for. So it's the variability accounted for by the treatment divided by the total variability, altogether, which is basically the treatment plus the error. And this is calculated by the formula t squared divided by t squared plus degrees of freedom. And that would give you r squared. If you took the square root of r, that would give you the correlation coefficient. If you wanted to find the measure of association between, the treatment and and whatever you're measuring. So it's t squared over t squared plus degrees of freedom, and you want to have a value of 0.25 or larger to show that you have a large effect. So there's no sample size in this formula, it's just based off of t. You could also calculate confidence intervals. So based on the sample mean and based on off the critical t-scores, you can calculate the confidence intervals and basically say that you're 90, 95% confident that the difference between the population and the sample takes on a particular value. So here's the T formula. T equals the mean, sample mean, minus mu, the population mean, divided by the estimated standard error of the mean. But if I want to solve for mu, I can just multiply out and subtract the mean, right? So what I can do here is I can rearrange this equation for mu, and mu will be equal to the mean of the sample plus or minus t, your t value, times the estimated standard error of the mean. And this is how you're going to calculate the confidence interval. You just rearrange it into the second formula. So mu is the mean of the sample plus or minus t times the standard error of the mean. And the t here is the critical t. So it's basically the value that's associated with whatever confidence level you're looking at. And the confidence interval is just a way of saying that we're 80 or 90 or 95% confidence that the true population mean lies in this interval. That's all it is. It's an alternative way to test the hypothesis. So in order to calculate confidence interval, we can look up the critical values of t in the table. So if I want a 95% confidence limit, confidence interval, with the degrees of freedom of 9, I can look up the score in the table. So in the table, I would look up alpha of 10.10, right? And I would want that to be two-tailed because the confidence interval is going to be on the positive side and also on the negative side. So I would look up a two-tailed value of alpha of 0.10 because that means that the rest of the distribution, the rest of the 90%, will go into the confidence interval. If I was looking for 95% confidence interval, I would want my alpha level to be 0.025. So I would want that, well, in each tail, it would be 0.25 in the right tail and the left tail, which is 5%. So I'd want basically 5% for two-tailed. And I would then find the critical value. So depending on what confidence interval you want, that will determine what your alpha level is. And your alpha level is going to be 1 minus the confidence interval. So if it's 90%, it would be 1 minus 90% would give you 10%, and then your alpha would be 10% two-tailed. If it was 95% confidence interval, it would be 1 minus 95%, so the alpha would be 5%, and I would want that two-tailed. And that determines how confident we are that the true population mean falls within that interval. So here we calculated an 80% confidence interval, and we're looking up the critical t values. And as you can see here, for 8 degrees of freedom, the critical t values are 1.397 and negative 1.397. So those two scores cut off 80% of the distribution. And that's how you would find an 80% confidence interval. Find the boundary points for whatever percent confidence you're looking for. So you're going to find the confidence level. You're going to use the t-table to find the value of t based on the degrees of freedom, your alpha level. And then you're going to solve the equation mu equals the sample mean plus or minus the critical value of t that you're finding for the confidence interval in the table times the standard error of the mean. And you can calculate that by the sample standard deviation and the sample size. And once you do that, you're going to have two endpoints. You're going to have a lower limit and you're going to have an upper limit for your confidence interval. And you're going to be, say, 90% confident that the population mean falls within these boundaries. Now, is that better than doing a basic hypothesis test? I don't think so, but uh, it's good for doing things like error bars on graphs that I talked about. That's useful. It can help show you exactly what's going on rather than just straight hypothesis testing. So it has confidence intervals have their uses, mostly for error bars that I see, but in some other applications. It does not make up for not testing a hypothesis formally. So you can't just do the confidence interval and say, okay, I did the confidence interval, I'm not going to do the hypothesis test. No, that doesn't work. You have to do the hypothesis test for everything. That if you want to add the confidence interval, it's going to strengthen your findings. So it's something you want to add in addition to hypothesis testing, not replace hypothesis testing with. Factors that affect the confidence interval. It could be the actual confidence that you're desiring. So if you want a higher level of confidence, like let's say you're going from 80% confidence interval to 95% confidence interval, right? That's going to increase the interval width. So you're going to have more options where the true population mean is going to lie. So the more confident you are, the wider the interval is. Also, the larger the sample, the smaller the interval is because you're dealing with standard error. And the larger the sample, the smaller the standard error. So that's going to decrease the interval. So your best bet is to pick a high level of confidence, which would increase the interval width for where you would find the actual population mean. And instead of like just sort of dealing with that, have a large sample because the large sample will shrink the interval and it'll shrink it more than it's being widened by uh, the actual setting a high level of confidence. And then once you've run the test, you're going to report it in the literature. So you may say that you found a significant difference, which is another way of saying that the null was rejected. Or you'll say that it was not significant, which is another way of saying you failed to reject the null. And then you're going to report the t-statistic. So it's t, the degrees of freedom are in parentheses, equals the value that you got from calculating the t-statistic. And then you want to report the exact probability if possible. So if you're doing computer work, you'll have the exact probability. You'll have the exact p-value. You report that. If you're doing it by hand, you want to report that it's less than 0.05 or less than 0.01 if it's significant. Because those are the two values we mainly use, 0.05 or 0.01. You could also have, besides non-directional tests, which we've been talking about, you can have directional tests or one-tailed tests, which are the same as the one-tailed test with Z. You have to find the critical value in either the positive or the negative tail. Let's look at a slide here to check our knowledge. The results of a hypothesis test are reported as follows. T of 21 is 2.38, P is less than 0.05. Well, how big is the sample? Well, the degrees of freedom are in parentheses, 21. If I add one person to that, that gives me the sample size, which is 22. So I know I have 22 in my sample. If P is less than 0.05, that's saying that basically you reject the null hypothesis. So it's significant. it's a significant effect, you reject the null hypothesis. So in this scenario, we rejected the null hypothesis with 22 subjects, and the only answer that fits that scenario is B. The null hypothesis is rejected using a sample of 22. That is obviously the answer. The answer is B. Reject the null, sample size is 22 because the degrees of freedom in parentheses is 21. So more true false. Sample size has a great influence on measure of effect size. Obviously that's false. Effect size is the effect of the independent variable regardless of the sample size. So effect size and sample size have nothing to do with each other. And the second one, true false, when the value of the t-statistic is near zero, the null should be rejected. Well, obviously false. The greater the t is, the further away from zero the t-statistic is, whether it's positive or negative, the more likely you're going to reject the null. And when the t-statistic is near zero, it's going to be in the middle of the distribution. There's really no chance of rejecting the null at that point. So when the value of the t-statistic is near zero, you do not reject the null hypothesis. So that's false. And that's what we have here. So effect size are not influenced by sample size, and you want your t-statistic to be far away from zero in order to reject the null hypothesis. And that's just a quick rundown of t, and t is basically like z, except that you're using the sample standard deviation, and the curve is different. You're going to have to look up the values in the table under the z table, and it's going to be harder to reject the null hypothesis, especially with smaller samples compared to z. So if you're going to use t, you want to use a big enough sample so that you're not penalized by the t distribution, which is really fat in the tails and flatter in the middle with small samples. And as the sample size goes up, the t distribution will approach the z distribution, which we already know. And it's easier to reject the null with z than with t. So hopefully that's a decent introduction. And if you have any questions, let me know. But just start doing problems, getting used to using the sample standard deviation instead of the population standard deviation. And the rest of the hypothesis testing process is the same, just a different critical value and a different standard deviation. That's it. So hopefully this is not too difficult. If you have any questions, please let me know. Send me an email, come to office hours, etc. Bye for now. See you next time.